my name is Pranav Sridhar, and in today's lab, I'll be analyzing the motion of my phone case falling with the help of Newton's second law of motion. As the object falls, we know one force that is for sure acting upon the object: weight. Hence, we set the net force equal to the weight. As we'll see later in the lab, this position versus time graph showed a clear non-zero net force. However, one force we didn't consider in our assumption that weight was the only significant force acting upon the object is drag, which we'll explore in more detail later. Before we discuss the lab in detail, let's talk about why we're interested in analyzing the motion of a falling object. The motion of a falling object is a crucial concept in physics. The fact that just by analyzing the change in position over time, we can learn a lot about gravity, which we know is used in almost every concept in physics, and it allows to create computer models to make predictions. First, we'll be exploring our initial assumption and then see how it looks with the drag force accounted for. As the phone case falls, you see the point masses that I've added. I did my best to place the point masses at the center of the phone case. However, as it falls relatively quickly, there are parts that are blurry, and it's also hard to find the exact center as it tilts a bit as it falls. When you look closely at the point masses, you see that they begin to space out more towards the end, and this is also reflected on the graph to the right. Now that we have our observed data, I went ahead to code a predicted model of the motion of my phone case. Note that this predicted model assumes that the only significant force acting upon the object is weight. As you can see, this is a snippet of my code which I used to set my initial conditions. The y component of the position vector has been taken from tracker, and mass was weighed using a balance. At the top of my calculation loop, you can see that we set the net force to the weight. Here's a graph that compares the observed and the predicted model of the phone case's motion. As you can see, the two lines are similar except for the little discrepancy. However, at the end, the predicted curve seems to get steeper. The reason to this is that we didn't account for the drag force. What is this drag force that I mentioned previously? It's the resistance force caused by the motion of a body through a fluid, such as water or air. Drag force is given by a formula shown on the slide. However, for our purposes, we'll set the constant to a variable b. On the right, you see the free body diagram, and the equation of the net force is presented at the bottom of the slide. We changed the initial conditions to account for the drag force. Given that I don't know the value to the constants mentioned in the last slide, I used trial and error to find the b value that will give us values similar to our observed data. In the new calculation loop, you see the formula of the drag force implemented, and the net force has been updated to weight plus drag force. In this graph, you see that the observed line and the predicted model with drag are very similar except for the small discrepancy. This solidifies our assumption that there was a drag force acting upon the object. The two main causes of the discrepancy mentioned earlier were probably the inaccurate positioning of the point masses and the inaccurate measurement of the height used for our calibration stick. The first issue can be fixed by using an object with a clear center that barely deviates from the vertical path. The other can be fixed by using something longer than a ruler, such as a tape measure. To answer the what does it mean question, I looked at the velocity versus time graphs from Tracker, and as you can see, the velocity graph with no drag force is linear, while the other isn't. It's clear that the model to the right can predict the terminal velocity. Terminal velocity is a constant velocity a free-falling object eventually reaches. In the graph with no drag, it was linear, so it wasn't ever going to reach a constant velocity. However, the graph on the right gets flat, signifying that it has reached terminal velocity. To answer the what if question, we can look at it both graphically and analytically. On the right, you see two graphs with the same initial conditions. However, the second graph has an initial velocity of 0, -3, 0 to represent the velocity of someone throwing it downwards as opposed to releasing it from rest. As you can see, except for the fact that the second graph reaches terminal velocity before the first, both have the same exact terminal velocity. This is confirmed when solving for the terminal velocity analytically. As you can see, the terminal velocity isn't dependent on the initial velocity. It is simply the velocity when the forces are balanced and the net force is 0. In this lab, we were able to model a falling object, learn about drag force, and calculate terminal velocity. Thank you for listening.